Hello YouTube, this is Wenn who does research for fun. In this video, I would like to go over my first authored paper titled Early Prediction of Soybean Traits Through Color and Texture Features of Canopy RGB Imagery, which was published in the journal Scientific Reports in 2019. In plant phenotyping, crop modeling is a significant research topic, since the whole point of plant phenotyping is to characterize crop traits, which are either directly measurable by sensors or might be indirectly predictable by coupling sensor data with advanced modeling techniques. During my master's program, when I had the chance to play with various sensors, I was always fascinated with the vision sensors and subsequent data processing. At the time, our research group already accumulated large sets of soybean RGB images along with agronomic measurements of the plants. And my committee member, Dr. George Meyer, introduced grade-level co-occurrence matrix-based texture features to me in one of our one-to-one conversations. So I thought to myself, can I do anything with these images and their features about the plant traits? Hence, the concept of this paper was born. I do believe this study captured a very important research topic, speed breeding, which can have huge implications for agriculture, but is still under-investigated to this day for field crops, in my opinion. Let's dive right into the paper. Current global crop production is facing a climbing demand, and the three key contributing factors include increasing population, growing meat and dairy consumption, and rising biofuel usage. By 2050, a 60 to 110% increase in world's agricultural production may be needed to meet the projected demand, which is known as the 2050 challenge. Unfortunately, research has suggested that globally, the average increase rates of yield from 1961 to 2008 for four major crops, maize, rice, wheat, and soybean, were far below the adequate levels to meet future demands. There are even concerns about our ability to maintain current crop yields facing the rapidly changing global environment. While more land clearing for agriculture and improving the productivity of existing cropland can both help increase crop production, the latter is preferred due to its environmental friendliness. Crop breeding aims to improve crop genetic makeup for more desirable traits such as higher yield. However, the improvement rate of modern crop breeding in terms of genetic gain is insufficient for the 2050 challenge. Partially, this slow improvement rate is due to the long crop generation cycles. As a potential solution, a newly emerged method, speed breeding, utilizes prolonged photoperiods and can increase the generation cycles of certain crops in greenhouse from 2 to 3 to 4 to 6 per year. However, greenhouses not only cannot fully mimic field conditions, but also have limited space and high operating costs. Therefore, field breeding is essential for selecting crop genotypes that are suitable for extensive agricultural production. Since field environment cannot be easily altered by humans like greenhouses, the concept of speed breeding cannot be directly replicated in the field, and alternative methods are still needed for accelerating field crop breeding research. Plant phenotype results from the interaction between plant genotype and environment, and reflects plant performance under a certain environment. Since the genotype of a plant does not change throughout the course of plant growth, relationships might exist between plant phenotypes at different time points. If plant end-season traits such as yield can be predicted using plant early-season phenotypic measurements, breeders then do not have to wait for a full crop generation cycle to finish before making plant selections, and field breeding speed can therefore be improved. In existing literature, early prediction of plant traits has already been investigated. For example, predicting soybean yield using normalized difference vegetation index measured at reproductive stages. Predicting sugar and fiber contents of sugarcane at maturity using the corresponding values measured months before harvest. predicting leaf nitrogen concentration of almond in summer using leaf nitrogen and boron concentrations in spring. Predicting grapevine yield using the number of berries detected at fruit development stages. To select a phenotyping method or sensor that is suitable for large-scale crop breeding research, it needs to be non-destructive and efficient. Unlike 3D vision sensors like LiDARs, RGB cameras have been widely employed in agricultural research. They are cheap and user-friendly, and are able to capture images in high spatial resolutions. With the popularization of smartphones, RGB cameras also have high accessibility. Additionally, there are a wide variety of well-established image processing and analysis techniques to extract features from RGB images. When it comes to digital image processing, there are two fundamental feature types. The first one is color. Color is the characteristic perceived by human visual system. The color of a plant is closely related to plant physiology and can indicate plant health and vigor. Some example applications of color features include plant segmentation, plant stress assessment, disease spot detection, and estimating plant traits such as ground cover, biomass, leaf chlorophyll content, and leaf nitrogen concentration. Many vegetation indices are also calculated based on RGB bands. The second one is texture. The essence of texture in digital imagery is the spatial arrangement of pixels with various grade levels, which conveys properties like coarseness, smoothness, randomness, or uniformity. Example applications of texture features include image segmentation, image classification, and pattern recognition. Among the various texture analysis techniques, texture features derived from grade-level co-occurrence matrix are the most popular because of their simplicity and adaptability. Despite color and texture features of RGB image have been extensively utilized in research, RGB image features in general have been rarely studied for crop trait early prediction purpose, and the value of texture features derived from RGB image transformations, such as vegetation index images, has never been investigated. Given that, the goal of the study was to explore the possibility of soybean trait early prediction using color and texture features of Canopy RGB imagery. More specifically, the objectives of the study included: first, select the modeling techniques that would provide the best prediction results. Second, determine the variable combination type that would provide the best prediction results, such as using only color indices, using only texture indices, or both color and texture indices, etc. Third, investigate whether the color and texture information of theoretical and empirical transformations of RGB images, namely images in alternative color spaces and vegetation index images based on RGB bands, could improve prediction results. And finally, identify which end-season soybean traits might be predictable through the color and texture features of early-season Canopy RGB images. Before we jump into the study, let's first familiarize ourselves with GLCM. GLCM was first introduced by Dr. Robert M. Herelick in 1973 in an article named Textural Features for Image Classification, published in IEEE Transactions on Systems, Man, and Cybernetics. GLCM was originally named Grade Tone Spatial Dependence Matrix, but now is commonly known as grade-level co-occurrence matrix. GLCM describes joint probability of pixel pairs at any grade levels, and therefore is able to represent image textures statistically. Even back in 2019, there were a large number of studies utilized GLCM for agricultural applications, many of which are listed in the table. GLCM can be mathematically expressed as P of ij d theta, where ij represent pixel intensities or the grade levels of two pixels in a pixel pair. D represents pixel displacement, or the distance between two pixels that can be considered as a pair, which is typically 1, meaning two adjacent pixels are considered as one pair. And theta represents scanning directions, or the direction along which the pixel pairs lie. And common scanning directions include 0 degrees, 45 degrees, 90 degrees, and 135 degrees. There are a few important considerations regarding the calculation of GLCM. First, calculating a GLCM over the full dynamic range of an image can be computationally expensive and therefore prohibitive. A common solution is image quantization, which reduces the number of grid levels in an image. For typical 8-bit images with 256 grid levels, common quantization levels include 8, 16, and 32. However, the trade-off of image quantization is the loss of information. Second, when calculating a GLCM, the distinction between two opposite scanning directions is typically ignored, such as from left to right versus from right to left, since the resulting GLCMs are simply the transpose of each other. Therefore, symmetric GLCMs, where both scanning directions are considered, can be employed. Third, before extracting texture features, a GLCM needs to be normalized through this equation by the sum of the matrix values. Lastly, the same texture features calculated from different GLCMs of the same image can be either averaged or treated as independent variables, although Dr. Haralick et al. Suggested to use the averages. Let's go through an example. On the left, we have a 4x4 image with 3 grid pixel levels from 2 to 4. On the right, we have a 3x3 GLCM layout for this image, where each value in the matrix represents the number of pixel pairs with a unique grid level combination. Depending on the scanning direction, as well as pixel displacement, which is assumed to be 1 here, we can generate different GLCMs from the images. Here shows 4 scanning direction scenarios for generating symmetric GLCMs, where each scenario involves 2 opposite scanning directions. And here are 4 symmetric GLCMs constructed based on the scanning directions. Finally, after normalization, the normalized GLCMs are ready for feature extraction. Now we are ready to jump into the study. In our experiment, a multi-sensor phenotyping system equipped with 3 Logitech webcam C920C was used for image acquisition. In total, 6,383 images over 6,039 soybean plots were captured. The soybean plots belonged to 35 yield evaluation experiments in University of Nebraska soybean breeding programs, and the images were saved in 8-bit PNG format with a 2304 by 1536 resolution. This table shows the locations, planting and harvesting dates of the soybean plots, as well as the data collection date, plot growth stage during data collection, and number of captured images at each location. This image shows where the locations are on Google Map. For end season ground truth, there were 7 quantitative traits, including yield, or seed volume in bushels per acre, adjusted to 13% moisture content. Maturity, or the number of days in between the planting date and the date when 95% of the pods have reached their mature color. Height, or the average length from ground to the tip of the main stem at maturity in inches. Seed size, or the seed weight per 100 seeds in grams. Protein, oil, and fiber, or seed composition measured through an Infratech 1241 grain analyzer. And 2 qualitative traits, including lodging, rated on a 1 to 5 scale based on plant leaning or downing, and seed quality, rated on a 1 to 5 scale based on wrinkling, defects, greenishness, and mold. Unfortunately, not all ground truths were available for all soybean plots in the study, and this table shows the number of images with corresponding ground truths available. For informational purpose, this table shows the Pearson's correlation coefficients between all the ground truth traits. while this table shows the corresponding p-values of the correlation coefficients. Image processing in the study was completed using MATLAB R2018B. For image pre-processing, the captured images were first contrast stretched to enhance contrast and improve color consistency across images. The contrast stretching was conducted on the RGB channels of each image independently by saturating the top and bottom 1% of all pixel values. And here is the mathematical expression of contrast stretching, where LO and UO are the original lower and upper pixel value limits, which are the first and 99th percentiles of all pixel values in image I of XY, and LN and UN are the new limits, which are 0 and 255 for 8-bit images. And we can turn an underexposed raw soybean canopy image like this into this. Next, soil background needed to be removed since it contained irrelevant information and could be treated as noise. When I processed the images, I learned the hard way that it was very challenging to perfectly segment the soybean canopies in all of the images, which were acquired under different lighting and shadowing conditions using just simple thresholding techniques. After many trials and errors, I came up with the following segmentation method based on multiple vegetation indices. First, 3 vegetation index images were calculated from each contrast-enhanced RGB image: excess green, EXG, modified excess green, MEXG, and color index of vegetation extraction, CIVE. The vegetation index images were then rescaled to the range of 0 to 1 respectively, and the difference image between MEXG and CIVE was computed to further enhance the intensity difference between plain pixels and soil pixels. 2 binary masks were generated by applying a fixed 0.5 threshold to EXG image and Otsu's threshold to MEXG CIVE difference image respectively. The 2 masks were then overlaid through a logical OR operation. Instead of using 0, NA values were used in the mask to avoid the influence of a large number of 0 when computing color and texture features. After cleaning up mask noise by removing objects with 300 or fewer connected pixels, the mask now could be used to remove soil background. And this image summarizes the entire workflow of image pre-processing. According to one of the objectives of the study, using each contrast-stretched canopy image as a base image. To investigate the feature value of transformed images, 4 common color spaces were selected as the theoretical RGB image transformation, and 20 vegetation indices based on RGB bins were selected as the empirical RGB transformations. Each color space contained 3 channels. On top of the original RGB color space, that gives us 1 plus 4 times 3 plus 20 equals to 35 transformed images. And this table shows the list of the selected color spaces and vegetation indices. Before extracting features, a canopy mask created during the image pre-processing stage was applied to all the transformed images. And here are the examples of the transformed images derived from the same soybean canopy image. And the color in each image corresponded to the image value range before the canopy mask was applied. Now, finally, we are ready to extract image features. For color features, using each transformed image as a base image with the canopy mask applied, 4 statistical color features were extracted, including mean, standard deviation, skewness, and kurtosis. During calculation, all NA values from the canopy mask were ignored. In total, 35 times 4 equals to 140 color features were extracted from each original canopy RGB image. For texture features, each base transformed image was first rescaled and quantized to 0 to 255 to reduce a computational complexity before canopy mask was applied. Then two symmetric GLCMs with 1 pixel displacement and 0 and 90 degree scanning directions were calculated respectively. During GLCM calculation, all NA values from Canopy mask were ignored. For each GLCM, 9 features were extracted, including maximum probability, mean, variance, correlation, angular second moment, entropy, dissimilarity, contrast, and inverse difference moment. And the same features from the two GLCMs were all averaged. In total, 35 times 2 times 9 divided by 2 equals 315 texture features were extracted from each original Canopy RGB image. When I conducted literature review for GLCM, I observed that there were huge amounts of confusions and inconsistencies among studies regarding GLCM feature definition and naming, so I listed the ones that I noticed in the article for clarification. The equations used for calculating mean and variance in the article where I and J were interchangeable were only valid for symmetric GLCMs. Angular second moment was sometimes named as energy, while energy was sometimes defined as the square root of angular second moment. Both 2 and Euler's number could be used as the base of the logarithm in the entropy equation. I actually emailed Dr. Haralick and asked if 2 or Euler's number should be used to calculate entropy, since in his original paper, the base was not specified, and I had seen both 2 and Euler's number being used in literature. I was very lucky to get a response from him, and he basically said both were fine. The entropy equation assumed 0 times log 0 equals to 0. Inverse difference moment was sometimes called inverse difference homogeneity or local homogeneity, but the denominator in the homogeneity equation was sometimes defined as 1 plus the absolute value of I minus j. For data analysis, the entire dataset was randomly split into 70% segment for model training and 30% segment for model validation. The predictor variables for modeling included the 455 color and texture features, which were normalized by mean centering and unit variance rescaling before modeling, and 2 additionally introduced variables, location and time, where location represented the 4 soybean plot growing locations, and time represented the number of days in between the planting date and the measuring date. The 2 variables were introduced to account for soybean plot location and data collection timing difference. All modeling work was done in R. 2 types of modeling techniques were employed in the study. The first type was regression modeling, and 5 techniques including partial least squares regression, random forests, cubist, artificial neural networks, and support vector regression were explored for the 7 quantitative ground truth traits. The second type was classification modeling, and 5 techniques including partial least squares discriminant analysis, random forests, linear discriminant analysis, artificial neural networks, and support vector machines were explored for the 2 qualitative ground truth traits. Model tuning was completed through 10 random segment cross-validation. All model evaluation was conducted using the validation data split. 3 metrics including RMSE, R-squared, and bias were used for evaluating the regression models, and 2 metrics including accuracy and kappa were used for evaluating the classification models. To investigate the study objective 1, what the best modeling techniques were, all 455 color and texture features were used as predictor variables, and all 10 modeling techniques were employed and compared, and the best modeling techniques were selected based on RMSE or accuracy. To investigate the study objective 2, what the best predictor variable combination was, the best modeling techniques selected in objective 1 were used, and 4 types of variable combinations were compared. Only 140 color features, only 315 texture features, all 455 color and texture features, and all 457 color and texture features, plus location and time. To investigate the study objective 3, what the value of color and texture features of RGB image transformations was. The best modeling techniques selected in objective 1 were used, and the best predictor variable combination selected in objective 2 was used. And models were developed and compared to objective 2 models, using features extracted only from red, green, and blue channels, since these 3 channels composed raw original RGB images, while everything else was a transformation based on these 3 channels. Depending on what the best predictor variable combination was from objective 2, since at this point we don't know the result yet, the number of features used for modeling could be only 3 times 4 equals to 12 color features, only 3 times 9 equals to 27 texture features, 39 color and texture features, or 41 color and texture features plus location and time. Now let's look at the modeling results. For objective 1, this table shows the model performances using the 5 regression modeling techniques for the quantitative soybean traits. And this table shows the model performances using the 5 classification modeling techniques for the qualitative soybean traits. Overall, no significant difference in terms of RMSE or accuracy was observed in between the modeling techniques. However, their R-squares or kappas fluctuated substantially. If we compare the worst model to the best model for all the traits, RMSE would increase by 5 to 42%, on average 16%, and accuracy would decrease by 9 to 11%, on average 10%, while R-squared would decrease by 8 to 62%, on average 31%, and kappa would decrease by 100 to 105%, on average 103%. Based on RMSE or accuracy, Cubist consistently provided better regression predictions than the other techniques except for fiber, and random forests performed the best for the classification predictions. Therefore, they were identified as the best modeling techniques. For objective 2, this table shows the regression model performances using Cubist and different variable combinations for the quantitative soybean traits. And this table shows the classification model performances using random forests and different variable combinations for the qualitative soybean traits. Overall, no significant difference in terms of all the metrics was observed in between the variable combinations for most soybean traits. If we compare the worst model to the best model for all the traits, RMSE would increase by 1 to 12%, on average 7%. R-squared would decrease by 8 to 42%, on average 15%. And accuracy would decrease by 0.7 to 4%, on average 2%. And kappa would decrease by 12 to 50%, on average 31%. Except for seed size and fiber, the variable combination of color, texture, and time and location consistently provided better results, hence was identified as the best variable combination for both regression and classification. For objective 3, this table shows the regression model comparison based on Cubist between 457 predictor variables and 41 RGB predictor variables for the quantitative soybean traits. Since in objective 2, the variable combination of color, texture, and time and location was identified as the best. And this table shows the classification model comparison based on random forests between 457 predictor variables and 41 RGB predictor variables for the qualitative soybean traits. Overall, all predictor variables consistently outperformed RGB variables. However, very comparable model performances were achieved by only using the RGB variables, which only brought a 0.04 to 7% RMSE increase, a 2 to 31% R-squared decrease, a 1 to 3% accuracy decrease, and a 2 to 50% kappa decrease. This result suggested that the color and texture information of RGB transformations could only bring marginal improvements to the models developed using solely the original RGB color and texture features. For Objective 4, using all 457 predictor variables, cubist as the regression technique, and random forests as the classification technique. This figure shows the final modeling results in terms of scatter plots and confusion matrices. Looking at the metrics, seed size, protein, oil, and fiber had small RMSEs. Yield and maturity had fair RMSEs, and height had a large RMSE. Yield, maturity, seed size, protein, and oil all had reasonable R-squareds, and height and fiber had low R-squareds, indicating the models were not able to explain large percentages of the data variances. All soybean traits had very small biases. Both lodging and seed quality had fair accuracies, however their kappas were very low, which might be due to the imbalanced data distribution where large proportions of low rating scores existed. So even if a model classified all data entries as low rating, accuracy of the result would be still high. A few interesting observations existed in the figures. The first are data clusters, which can be observed for maturity, seed size, protein, and oil. And the clusters themselves represented soybean plot location and soybean population differences. Additionally, outlier entries where very low fiber values existed. Since protein, oil, and fiber were all measured simultaneously, we determined that the low fiber values were unlikely to be caused by instrument malfunctioning and therefore should still be valid. Based on the overall consideration of the prediction results, we identified yield, maturity, and seed size as the potential soybean traits that might be early predictable. Given the results of the study, there are several key findings worth discussing. First, texture features always provided better predictions than color features alone, which suggested that texture information might be more meaningful for early soybean trait prediction. Second, the combination of both color and texture features did not consistently outperform using color or texture alone for 5 soybean traits in terms of RMSE, which might indicate information overlapping between the two feature types. Third, the introduction of location and time variables significantly improved prediction results for 7 out of 9 soybean traits. This suggested that accounting for factors like soil type, climate differences, and the number of days after plant emergence was crucial, as these could significantly impact plant appearances. Finally, RGB image transformations offered only marginal improvements to prediction results compared to using features from the original RGB images. This is likely because linear or nonlinear relationships exist between these transformations as well as the original RGB channels, leading to similar or overlapping information. This speculation was confirmed by this figure that shows the histogram of correlation coefficients between 455 color and texture indices of all 6,383 RGB images. That is 455 squared equals to 207,025 coefficients, where a considerable amount of strong positive or negative correlations can be observed. Our study suggested the possibility of early prediction of end-season soybean traits using color and texture features from early-season Canopy images. The true reason for this possibility, however, still remained unknown since this research topic was rarely explored. Existing literature has simply proposed a black box relationship for Canopy parameters and Canopy images. As an attempt to rationalize the study findings by connecting plant science with digital image processing, we proposed that plant developmental traits such as plant architecture and leaf features can determine plant overall performance and are reflected in early-season Canopy images. Therefore, it can be logically assumed that the Canopy color and texture features indicate or represent these plant developmental traits as well as the interactions between them. We identified the following plant developmental traits that can be represented by canopy color and texture information, and are the primary contributors to canopy color and texture index variations. The first one, leaf color. Leaf color is closely associated with plant vigor and health, reflects biotic and abiotic stresses caused by diseases, nutrient deficiencies, etc., that eventually lead to chlorophyll destruction or formation failure. Considering healthy leaves should have uniform green color distribution and therefore small image channel standard deviations, non-green, necrotic lesions on leaves can lead to larger channel standard deviations because of the non-uniform color distribution, and chlorosis can lead to channel mean shifts due to the overall color change. The second one, leaf shape. Leaf shape can be affected by many factors such as genotype, leaf angle, branch angle, insect damages, plant diseases, environmental stresses, etc., and can influence plant light harvesting efficiency and indicate plant health. Since leaves are the fundamental subunits that give the overall canopy textural appearance, the change of leaf shape will lead to the change of canopy texture features. The third one, leaf size. At the same growth stage, leaf size can denote plant growth rates. It is also directly related to photosynthetic capacity, since it affects cell number and chlorophyll content. Large leaves can give plant canopies a coarse texture appearance, while small leaves can give a fine look to canopies. This canopy appearance difference would eventually affect the canopy texture features. The fourth one, leaf area density. Leaf area density describes how closely leaves are distributed, therefore directly influences photosynthetic capacity as well as photosynthetic efficiency by affecting the quantity of light interception. Additionally, leaf area density indirectly shows the number of stems or branches, which is usually negatively correlated with the plant height and lodging. High leaf area density can add complexity to plant canopy texture, whereas canopies with low leaf area densities would have simpler appearances, which would reflect in the canopy texture features. The last one, plant density. Given consistent seeding rates, plant density in images reflects emergence rate and early plant population. It also can affect plant photosynthetic efficiency as it is plant spacing dependent. Higher plant density leads to a more uniform canopy texture, while lower plant density results in an irregular texture. In general, plots with fewer plants emerged are expected to have lower final yields. As a final summary, the color and texture indices derived from early season canopy images are hypothesized to represent various intertwined plant developmental characteristics, such as leaf color, leaf shape, leaf angle, branch angle, leaf size, plant growth rate, leaf area density, stem number, branch number, germination rate, etc. These characteristics, in turn, indicate plant vigor, plant health, plant drought resistance, plant photosynthetic efficiency, plant photosynthetic capacity, etc. at early growth stages, which ultimately impact end-season plant performance. Regarding the limitation of the current study and future research directions, 256 grade levels were used when calculating GLCMs. Although images with more grade levels contain more information, research has indicated that the classification ability of some texture indices can decrease with an increased number of grade levels. Future studies can investigate different levels of image quantization such as 128, 64, 32, 16, or 8 for crop trait early prediction and comparing prediction results to determine the optimal level. Similarly, 1 pixel displacement was used in the study for calculating GLCMs, while future studies can investigate the influence of larger levels of pixel displacements. Only 2 scanning directions were used in the study when calculating GLCMs. Future studies can utilize all 4 scanning directions and average the texture indices to create more comprehensive representations of a plant canopy. Our image dataset lacked color calibration. Therefore, the image color could be inconsistent across different images due to different lighting conditions. A common practice for image color calibration involves capturing a camera calibration target, such as color checker, in all images. However, implementing such a target effectively in a high-throughput phenotyping system for thousands of plots remains a challenge for future research. The cameras used in the study were unable to capture the fine vasculature of soybean leaves. Vasculature features such as vein density and diameter are crucial for plant mechanical strength and nutrient transport, which further impact photosynthesis. In future studies, when images with sufficient spatial resolution are captured, their texture indices could potentially serve as good indicators for subtle leaf vasculature differences among various plant genotypes. Aside from the modeling techniques that were compared in this study, other machine learning methods, such as deep learning techniques, can be examined in the future as they have been demonstrated to have outstanding performances. The imbalanced data distribution for lodging and seed quality led to seemingly high accuracies. One way to mitigate data imbalance is to merge categories with the small sample sizes. We chose not to merge the small classes in the study, as 5-point scale scoring is common in plant breeding and provides more desirable and informative results for breeders. Our soybean image dataset was collected at central and eastern Nebraska areas during the summer of 2016. To confirm the validity and applicability of crop trait early prediction through RGB imagery as a general concept, experiments for various crops under diverse environments across multiple years are needed in future studies. In conclusion, for soybean growing at central and eastern Nebraska in 2016, for the purpose of soybean trait early prediction through color and texture features of Canopy RGB imagery, among the 10 compared modeling techniques, Cubist was the best regression technique, and random forest was the best classification technique. Using both color and texture indices as well as variables that account for soybean plot location difference and data collection timing difference could provide the best prediction results. Theoretical and empirical transformations of RGB images did contain additional color and texture information that could bring marginal improvements to prediction results. Yield, maturity, and seed size or the soybean traits that might be early predictable using color and texture features of early season Canopy RGB images. This paper was the second and last paper that I published as a master's student. It was actually published after I did my master's defense and was already enrolled into my PhD program. This study taught me that it is entirely feasible to conduct research projects just based on the dataset, and expensive hardware and in-field experiments are not absolutely necessary for all research topics. That is why today I can still conduct research as an independent researcher without having the access to university resources, since I mostly choose software-focused research topics. I had fun conducting this research project, doing a really thorough literature review, learning about GLCM, making the figures and writing the paper. The email exchange with Dr. Herelick was certainly a magical moment for me. Verifying an ambitious but empty idea just out of my head to be actually feasible is certainly a cool experience. To this day, I still believe the core concept behind this research, speed breeding, but for field crops, has tremendous potential. If I have the resources and can do it again, I would acquire a very large high-quality image dataset consisting of multiple crop types and multiple growth stages across multiple years, color calibrated, and for sure I would just use deep learning for modeling, a big convolutional neural network for both regression and classification, and see when the dataset is large enough to represent the real world with all the complicated variables and uncertainties, whether this field crop trait early prediction idea can still hold up. I hope other researchers can carry on my vision and continue exploring this research topic further. That is enough chit-chat from me. I thank you for watching the video up to this point, and I hope you have enjoyed my talk. I'll see you in my next paper.